Hello everyone, welcome to Dakshana e-classroom programs. In last lecture, we talked about different topics related to elasticity, that is a rod as a equivalent spring, elastic potential energy stored in a rod, variation or different varying loads applied to a material wire, then how it's a sigma versus strain, means stress versus strain graph was plotted, and from there we discussed about different points and their meaning, about that they tells about the behavior or properties of material. So that way we discussed, we missed some few points. Basically I was supposed to start next topic is, that is viscosity, but before that let me tell you a few more points. One is elastic after effect, another elastic fatigue. So elastic after effect is that I told that when we are removing the deforming force, then bodies have tendency to regain their original shape and size. But the point is that, let's suppose if I am stretching a body, some deforming force is applied, deformation is there, deforming force is removed, then all material bodies do not regain the original shape and size immediately, right? They take some time in regaining that original shape and size. So this delay in regaining the original shape and size by the bodies is termed as elastic after effect. So material bodies take some time to regain their original configuration on removal of deforming force, and the delay in regaining the original configuration by the bodies on the removal of deforming force is simply termed as elastic after effect. Another thing comes is that, let's suppose some material is there, some body is there, it is having some sufficient elastic strength, but what happen actually, whenever a body is repeatedly going through strain, then its strength keep on decreasing, or you can say strength decreases. So that is termed as elastic fatigue. So the loss of strength of material due to repeated strains on the material, and this is termed as elastic fatigue. Elastic fatigue means whenever it is going under the body, or the body is treated or going through a process of repeated strains, then it's losing its strength, and this is termed as elastic fatigue. Okay, so this is the reason because of which many times the bridges are after some time, because they are going repeated this strain and all those process, so after a long time of use they are sometimes declared as unsafe for the public transport. So that is also one of the reason. And then next we talked about different modulus of elasticity, and we Poisson's ratio in the last class. Actually those things are related, and the relation between them I'm directly writing. So if Y Young's modulus, V bulk modulus, eta is the modulus of rigidity, and sigma is a Poisson's ratio, then they are related, and why the relation between them you need to remember them. Sometimes direct problems are asked based on it, so if you're remembering the result you will be beneficial, you will be able to solve it. So Y Young's modulus is related to 3 times of B, that is bulk modulus, bracket 1 minus 2 sigma, and similarly Y is also related to modulus of rigidity, that is Y Young's modulus equal to 2 times of eta, bracket 1 plus sigma. Just from these two, eliminating Y and sigma, basically we get these relations also. So Y is equal to 9B eta, bulk modulus into eta, divided by 3B plus eta, and similarly sigma we get 3B minus 2 eta divided by 6B plus 2 eta. So basically this is where your elasticity things almost get over, but there are few topics, actually few things are there that are actually not exactly in the syllabus from the NTA side, but still it's important, sometimes questions are asked based on it. So that is another small point, that is torsion of cylinder or wire. So what it mean exactly, and let me tell you. So let's consider this is a cylinder, and simple this, and it's this is the center, I am drawing it. So this is simply was I have considered one feet, okay, this is the part of one cylinder. Now initially it's in this shape and orientation. Now what is happening actually, if this end is fixed, one end of the cylinder is fixed, this is fixed, and sometime like this end is tried to, or we are trying to rotate the lower end, then what will happen actually, this line, if I have drawn it, it will twist by some angle, so it will come in this orientation actually, it will be twisted by some amount, and orientation of this line will be like this, so it will be in this manner actually. So here it will be like, let's say O, this is O prime, this is P, this is Q, then Q will be shifted to some Q prime. Is it? Cylinder is there like this, you can just consider. So now here I'm fixing this one end, this end is fixed, and this end is twisted. It's not twisting, I know that it's difficult actually. If it is a long wire, then you can like twist it by little bit angle, but here just you can easily imagine from this diagram. So initially this was like OO prime is the axis of the cylinder, and it was PQ was the vertical line I have just drawn for the reference on the cylinder. Now what I am trying to do is, this upper end is fixed, this end is fixed, it's not free to rotate, and this end, lower end, is now a couple force, torque is basically applied on this like this way. So that will try to create some basically a strain or shear strain in this cylinder. So there will be some shear strain. This I will write, this shear strain is phi, this is the shear strain, and this is called basically shear angle. And the lower surface, the face of the cylinder will be twisted by angle. So this angle Q O Q prime, this is called angle of twist. I'm writing it angle of twist, this is, let's say, theta. Okay, so this is called like complete is termed as torsion of cylinder or wire. So here the torque required is it, we write here one called torsional constant of cylinder or wire, or we write it also, this is the torque required for unit angle of twist. So that it is denoted by letter C, and this comes out to be actually pi eta into r raised to power 4 divided by 2l. Okay, so this depends on actually pi, just one constant, eta modulus of rigidity, r is the radius of the cylinder. So let me write r is the radius of cylinder or wire, l is the length of cylinder, this length is taken as L, and this radius is taken as small r. Okay, eta is the modulus of rigidity of the cylinder, then C, that is also termed as torsional constant of cylinder or wire. It's related to basically eta, pi, and r raised to power 4 divided by 2l. And here you can see easily we can have the relation between this theta and phi. Theta is what? Angle of twist. Phi is called shear angle or angle of shear. So here Q prime can be related actually. So I can write Q prime is equal to what? This is equal to R into theta, and Q prime is also equal to L into phi. This length, arc length, R into theta. Here this is theta, I have already mentioned, and this is phi, then its length is L, then Q prime will be also equal to L phi. Now from here I can write R theta is equal to L phi, and here you can write theta is equal to L by R multiplied by phi. So that is how they are related. This is called torsional constant of the wire, and here, so if torsion constant of the wire, then tau can be written as basically C into theta. The torque required to twist the wire by angle theta, that is related this way. So now if it's being rotated, then some work will be done. So work done in rotating or twisting the cylinder by angle theta, that can be written as half c into theta square, because tau into d theta will be the work done, torque multiplied by angular displacement d theta, and integrating it c theta d theta, we will get this half c theta square will be the work done. So this is about torsion. Simple things here. One end of the cylinder is capped fixed or wire capped fixed. Another end, on another end, a couple force is applied, a torque is applied, which is creating some twist in the lower face, and along the length some shear strain is produced. So we measure this shear angle, shear strain. Here this angle, the base here OQ has rotated, twisted by some angle called theta, that is called angle of twist. Then the C, that is called torsional constant of the wire, is related to these quantities in this manner, and here C is called torsional constant. So C is also the torque required to a torque required for unit angle of twist. In this this is the relation. Just sometime, like if you are required, you should keep those things in your mind. Theta, C and tau are related in this manner. So tau will be equal to C into theta, and the work done in twisting the cylinder by angle theta can be expressed as this way. Similarly, there is one more point left, that is thermal stress. Let me explain you what is that. Okay, so the next topic is thermal stress, and before explaining thermal stress, let me tell you or talking about explain you thermal expansion. Is it thermal expansion? So you must be familiar with this thing that on heating most of the material expand. I would say most of the material, and this is the reason. That's why, like, if you might have observed the difference between the electric lines, is it wires, in summer they comes basically loose, their sagging is there, their height also reduces because they become loose because of expansion due to heating. In winter they again become little bit tight. Okay, there are many more example about it. So what exactly happened? So we told you that in any substance the material actually, is it, so here this is the U versus R, potential energy versus R is the separation between two molecules or atoms. So this is, so they stay normally at some angle separation R naught at equilibrium position. Now what happens, let's say two atoms are there, they will be staying with some separation between them R naught in equilibrium. Means if they are not disturbed by any external agent, by any external force, they will simply stay together at this much separation. Now what happened, sometime we are pulling, some deforming force is applied, so because of that the separation will increase, and that result in, again, because this bond act like a spring, so that again some restoring force is developed between these two. So when you are releasing it, they regain their original shape and size, right? Another thing is if I'm heating, in that case what happen, actually both of these atoms or molecule acquire some kinetic energy, so the potential energy also decreases, is it, kinetic energy they acquire. So because of that this graph also like shift somewhat little bit here, and this equilibrium position changes actually R naught prime, is it, due to heating, right? What will happen, equilibrium both, I will say kinetic energy of both atoms and molecule will increase, and this changes the equilibrium position, is it, or the equilibrium separation between them increases. So what happened actually, between any two molecule or atom, the equilibrium separation, if originally they were at, let's say, T1 temperature, they were at this much distance. At T2 temperature, some temperature is increased, they will be like at this much distance. They will be like desired, they will be interested to stay at little bit larger because of the kinetic energy. Now kinetic energy has increased, vibrations are increased, so their equilibrium position shift away actually. So that's why it shift away from R0 to R0 prime. So what happened actually, let's say this is one rod. At atomic level, what I can say, it has like many atoms in this manner, and they were staying here with some separation between them. But when this is, let's say, at temperature T0, if I am heating it temperature T0 plus some delta T, what will happen? The equilibrium separation between each of these two molecules will increase. So because of that, the equilibrium separation between each of these two molecules increases. So effect is that if its original length was, let's say, L0, now at this point its length become L0 prime, and you can see L0 prime is greater than L0. This is called thermal expansion, right? So this is called thermal expansion, and I hope you are clear that why it expand on heating. So every material expand on heating. One more point, important point, is that every dimension expand on heating. Is it? Every dimension of a material expand on heating. This is important point because sometimes, like here, this is just for your interest. Let's say this is one sheet, a metal sheet, one small hole is there, right? Now sometimes questions are asked, if this sheet is getting heated, what will happen? This will expand, this will expand. What will happen to the hole? It will contract or it will expand? If you're remembering this point, every dimension of all the material expand on heating, then the situation you can easily answer it. It will be like this. I mean, like, let me draw it here. Only it will be expanded, both length and width will be expanded. Hole will not contract, hole will also expand. So dust will be the shape of this metal sheet on heating, on like rising its temperature. So the thing is that this is the mechanism, this is the like reason why on heating substance material expand. And here if I'm talking about the linear expansion, is it linear expansion? So if let's say T0 is the temperature and L0 is the length and alpha is the coefficient, thermal coefficient, we call it thermal coefficient of linear expansion. In that situation, this change in length on heating will be like how much material will expand, because you can see if there are 100 atoms, is it, then expansion will be corresponding to 100, because between any two atom separation will increase. So overall more number of atoms are there, more expansion will be there. So I can write the expansion will be directly proportional to the length, will be directly proportional to the rise in temperature, and this proportionality constant is replaced by alpha, that is called thermal coefficient of linear expansion. So delta L is coming out to be L0 alpha delta T. Delta T is the change in temperature. Delta L can be written L0 prime minus L0. This is equal to L0 alpha delta T. This implies L0 prime is equal to L0 1 plus alpha delta T. This is the final length. So on heating, the expanded length will be given by L0 prime equal to L0 means initial length 1 plus alpha delta T. Now remember one thing here actually. In this situation, which is the original configuration? So original configuration, or I would say the natural length, is it? Natural length. Let me just erase this part. which is the natural length of the rod? If I just simply talk about, because this is also quite important to understand thermal stress. So here comes one natural length. Natural length here means if we are not applying any external force, no force, nothing, torque, nothing is applied, then in what shape, size, configuration a body would like to stay, is it? Similarly, if I say if I am not applying any external force, then what is the length at which the rod will be staying, or what will be its length without any external force? That is termed as your natural length, is it? So the length of, or I would say the dimension, is it? Here I am writing natural length, so that's the length of the body without any external force or torque. Means if no external force, no torque, no nothing is applied, then what will be its length? That is termed as its natural length. So at T0 temperature, I would say L0 is the natural length. At T0 temperature, natural length will be equal to what? L0. Then at T0 plus delta T temperature, what is the natural length? The natural length is L0 prime. At T0 plus delta T, natural length of this rod will be L0 prime. Remember that, is it? So means in this situation, I would not say there is some strain because the body has expanded. Remember that. Strain will be when like body want to stay in one length, but we are changing it by applying external force, deforming force, we changing its natural length. Then there will be some strain. If the body is in its natural length, there is no strain in the body, is it? So in natural length, strain in the body will be 0. Means it's in original configuration, there is no change in original configuration, then where is the strain? So that's why whenever the body is in natural length, a natural configuration, there is no strain, there is nothing. Understood? Okay, so this is up to like and linear expansion. So exactly same manner, if a body is having like say 2D, maybe some seat or plate, something like that, then it will expand in both dimensions simultaneously. So then we will calculate actually aerial expansion. So these are small things I am writing. Aerial expansion means its area is, let's say, A0 at temperature T0. So what will happen actually if temperature is increased, let's say by delta T, then A0 prime will be A0 1 plus beta delta T, and beta is called thermal coefficient of aerial expansion. And so on is the volumetric expansion, And so here if we are having one body, is it? So V0 is the volume at temperature T0, then on heating I can write if temperature is increased by delta T, then its volume V0 prime will be V0 into 1 plus gamma delta T, where gamma is called thermal coefficient of volumetric expansion. Okay, so simple thing, if it is a linear body, linear one dimension, heating, that will expand. two dimension, both will expand. That result means area will expand. So areal expansion can be directly written as this. Similarly, if a solid 3D body is there, on heating its all three dimension will change. That result in volumetric expansion, so its volume will increase. So that can be volume V naught prime is the volume of the body at T naught plus delta T temperature. That is V naught initial volume at temperature T naught bracket 1 plus gamma. Gamma is the thermal coefficient of volumetric expansion. These are just for your information. Mainly here we require this linear coefficient or linear expansion. Now let me tell you thermal stress, what exactly it means. Okay, so now let's consider we have one rod, okay, whose temperature is T naught, its length is L naught, alpha is the thermal coefficient of linear expansion. This end is fixed, this is free. Now what happens if temperature is increased by delta T? What will happen? Simply rod will expand. L naught prime can be written as L naught 1 plus alpha delta T. Just imagine it. Now think about it. Do you really think there will be some stress, any force anywhere? Can you feel it here now? I think the answer will be no. And that's true. Because there is no, why there will be force? So now what will happen actually? At this temperature, is it? If this was the, or I would, let me write it here only. So it will expand by some amount, this, and this is the L naught prime length at temperature T naught plus delta T. So in this situation, simply natural length of the body has changed. At T naught temperature, natural length was L naught. At T naught plus delta T temperature, now length become L naught prime, and that is equal to L naught 1 plus alpha delta T. Now what will be the situation actually? Just imagine the same rod and just a small gap, not much. This here also some like support is capped, means right now there is no force between like both ends, no force by both ends. They are just like capped, no force, no nothing, pressure is there from either side. So this is same at T naught alpha L naught length, and now it's heated, right? What will happen? This rod would like be expanding if there was no support, so it will try to push the support away, but because these are fixed, so it would like want to expand here, but it's not allowed to expand. So in this situation, the rod is not allowed to expand. Can you just imagine? Can you feel the force on this support, I hope you must be feeling it. And that's the thing actually, where because this force on this, like rod will be applying force on the support, and support will be also applying force on the rod. So now in this situation, this force is arising because of change in temperature of the body. Understanding? So the force per unit area that is developed in this rod is simply termed as thermal stress. I hope you are getting the point. So in this situation, the rod was allowed to expand freely. So that's why whenever there is free expansion taking place, there is no stress, there is no strain, and you must be even understanding why there is no strain, because its natural length must be L naught prime at temperature T naught plus delta T, and it is there in that length. And where is the strain? And if there is no strain, there is no stress, nothing. And you can even feel, we can't feel any force anywhere here. So that is the thing. So means free expansion, no stress, no strain. But when the expansion is restricted, right, like the rod is not allowed to expand here, the rod would want to expand, but it's not allowed because of these two fixed support. In this situation, rod will experience some force due to these supports. So here, on heating support, like, is it, or I would say both support at end will restrict the expansion of rod, and I will say by applying force on the rod. So this force will create stress, and that is termed as this force per unit area of cross section of rod is called as thermal stress. Next point is how we can calculate it, right? Yes, we can calculate it. So here, let's say Young's modulus is also given actually, right? And Young's modulus does not changes much with temperature. We will take it's almost constant for this situation and this situation also. So next point is calculating thermal stress. I hope by this time you must be clear exactly like what does it mean thermal stress, or what do you mean by thermal stress. So calculating thermal stress, right? So in this situation now, what is the length of this rod? Now the force, okay, just one, like I have not write it, at temperature T0, length L0, and alpha y, everything is there, at temperature T0 plus delta T. What is the length of the rod here? Length of rod, it's equal to L0. But is it its natural length? And that's not. The natural length equal to L0 prime, that is L0 1 plus alpha delta T. So means this length is higher. That means actually the rod is not in its natural length. It has been compressed by some amount. How much is it? So the change in length equal to L0 prime minus L0, right? Here the rod has been, you can just imagine it like this, that rod has been compressed by, so this is T0, L0, alpha y. So T0 temperature, length L0, T0 plus delta T, T0, then length still L0, but natural length will be L0 prime equal to L0 1 plus alpha delta T, right? So actual length is L0, but the natural length should be this. So that means we can understand, we can just imagine, you can understand it in another way also. Let me allow it first to expand it for this length, then by pressing this I am bringing the length to original length. That is also same thing. So means now strain has been created, has been developed in the rod. So now strain, we call it thermal strain, or this will be thermal strain. So what will be that? So strain is same, delta L divided by L. Next thing is here, what should be this length here? Is it ideally delta L, I will write it's L0 prime minus L0, and here or you can write it basically L0 minus L0 prime, and L will be equal to actually L0 prime. So ideally I should write but we take it like magnitudes, then I will take it mod. So in this situation it will be like L0 minus L0 prime will be L0 alpha delta t. This is L0 alpha delta t, and I should write it L0 prime, that is equal to 1 plus alpha delta t. But the thing is that ideally, remember it, ideally this is the formula for thermal strain. For thermal strain, but this expression seems a little bit lengthy. Another point is this quantity is very small. This is very small. So what we do, we make some approximation. Approximation by simply ignoring it to 0. In that situation, thermal strain become L0 alpha delta t divided by L0, and that is equal to simply alpha delta t. This is your thermal strain. So remember it, ideally this is the proper definition of thermal strain, but in books, most of the books, you will find it simply this, that is by approximation. So we write it in this manner, and this is your thermal strain. So now we got strain, doesn't matter whether it's because of heating or whatever it is, but strain is there. So means strain and stress, they are related, and we know the relation, is it? So then we can get the corresponding thermal stress developed. So epsilon thermal, we got thermal strain is equal to what? Alpha delta t. Then Young's modulus is equal to stress divided by strain. Now when it is because of thermal, then we will write sigma thermal, epsilon thermal. So this implies sigma thermal is coming out to y into strain thermal. Sigma thermal is equal to y, and this is what? Alpha delta t. This is thermal stress. So I hope you must be clear with the meaning of thermal stress. So when a stress will be developed, when is thermal stress will not be developed, that must be clear to everyone. Let me give you just some logical examples. So just consider here this situation. This is the one rod, and this is some, let's say, gap. This gap is B, or let me write it A, some gap, and it's same thing, L0 rod length, L0 temperature, T0 alpha, Y, everything is there. Now rod is heated by delta T temperature, so that temperature rises by delta T. Now what will happen actually? Change in length, I will write the rod will start expanding, so that is equal to L0 alpha delta T. This will be the expansion if the rod is heated by delta T. Now there will be different situation. So case A, when delta L is less than A, what it means the gap is, let's say, 5 centimeter, but the heating due to expansion due to heating is, let's say, 3 centimeter. Then what will happen? Still gap will there, the rod will expand up to here, and still gap will be there. So do you think there will be any thermal strain? There will be any thermal stress? What do you think? I think you should be in position to answer this, because here the rod is allowed to expand freely, so that's why there will be no strain, no stress. B case. Understood? In this situation, because freely expansion is there here, this support is not working, it's not doing anything, so there will be no stress, there will be no strain. Next situation, delta L is less greater than A. Now it's heated by more temperature, so that this delta L, the expansion is less than A, In this situation, what is thermal strain, what is thermal stress, is it? So now here you can see up to A expansion it is freely allowed, so means up to the length or up to the expansion A there will be no strain produced in the rod, but once it want to go beyond that, only that expansion is restricted, so the strain will be developed only. Let's suppose if the support was not there, then it would be expanding up to here, is it? So this is the total delta L, but it's allowed to expand up to A. So how much restriction is there? Delta L minus A is the restriction. That will create only strain, right? So I will write here, I hope you are getting it. My point is simple. Whenever free expansion, whether it's partially or completely, till the time there is free expansion, there is no thermal strain, no thermal stress. It will be simply changing its natural length. So the body will be still in its natural length, but as temperature rises, the natural length also changes. No stress, no strain, nothing. But whenever some restrictions are imposed, it is not allowed to expand, only then it will create some thermal stress or strain. So in that situation we understood, because it was completely restricted, so that was the strain and this is the stress we got. In this situation it is restricted but partially, so that partial restriction will only create thermal strain and thermal stress. So in this situation I can write, if delta L is greater than A, so up to A it will be allowed, up to A it will be allowed expansion, right? So thermal strain will be equal to what? That I will write delta L minus A divided by original length, so I am writing it simply L0. This will be your thermal strain in this situation, and then thermal stress is equal to Y into epsilon thermal, and this you can write delta L can be written L0 alpha delta T minus A divided by L0, this multiplied by Y will be your thermal stress. So I hope this example make things clear, that by this time what exactly the meaning of thermal stress, when it developed, how it developed, when it will not be developed, that all should be clear. So this is all about basically thermal stress, and here also we end the chapter, that the part that is called elasticity. Let's continue here next with the viscosity topic, that is about liquid. Okay, so the next topic is viscosity, and viscosity is actually defined for fluid. So fluid you can understand easily. Fluid is substance, we can define fluid with substance which can flow, or I can say which cannot bear any amount of shear stress, that is termed as fluid. So in fluid basically there comes liquid and gas, both are termed as gas, are called as fluid. So the viscosity term is defined for fluid actually, and friction we are very well familiar with that term. So whenever like two rough bodies there and their surface in contact, and whenever there is some relative motion between two bodies is taking place, then one body opposes the motion or relative motion of other body, and by the force we call that friction. So friction is basically resistive force, opposing force between solid bodies, right? Sort of like similar thing happen in case of fluid, and that too, why, let me tell you. So here right now I am mainly talking about liquid. I will come for viscosity for both. So in liquid, there are basically, if it is filled in some containers, so first two things are there. One is called forces are there. So cohesive force and adhesive force, ADHE. What are these cohesive force and adhesive force? So we know actually solid molecule, two molecule also attract each other. I mean, like, they are bonded together by a force depending on the type of the bond, but still there is, the bond is quite strong, is it? They will not allow to move. And when the force between two molecule become little less compared to solid, then it become like free to move and it become liquid. Similarly, if the force between two molecules become very less, then the phase of the substance is gas, right? So gas, so coercive force is what? It is the intermolecular force between the molecules. It can be atoms also, atoms of same substance, that is termed as cohesive force. Just simple example, consider, let's say this is a container, is it, and in which some liquid is filled. Now what will happen actually here? So between two liquid molecule, I will say there is some force, is it? Liquid molecule, these liquid molecules are there, they will be applying force on each other. So these will be like applying force on each other. So the force between the molecules or atom of same medium, or I will say is it of same substance, is termed as cohesive force. So force between the water molecules will be a cohesive force. Similarly, adhesive force is the force between molecules or atoms of different substance, is called adhesive force. So what happened actually here? This is the wall of the container. So the wall of the container will also have some molecules, some atoms. So let's say I'm and just wait, there is some fluid filled, and now I'm this part zoom. So then what will happen actually, this is, and here it will have molecules, is it, of solid substance, and the molecules of liquid will be also there in the nearby, is it? So let's say I would say here these are, this side it's like solid molecule, and these all are liquid molecules. So between these molecules also there will be some force, and this is your adhesive force. In simple terms, I will say, if between two molecules or there is always force, depending on when the force is strong, molecules or the material becomes solid. It's less strong, it becomes liquid, and the force between two molecules is very less, then it becomes gas medium. So in gas medium also there will be one medium, is it, all gas particle. In liquid also there will be all liquid and a solid. So whenever the force between the same liquid medium particles between them, we will call that as cohesive force. The force between liquid molecule and solid molecule will be termed as adhesive force, right? So this is just term. Now what happen actually, so when a fluid or a liquid is flowing through a tube or maybe on some surface, is it, so let's say then what will happen? Some molecules of the fluid will be in contact of the pipe, is it? So let's consider here. So let consider fluid, basically here that's liquid is flowing over the surface, is it, of a large plate. So this is a large plate and over which the fluid is flowing. Okay, now what will happen? So this is fixed, this is fixed, right? And then over which the fluid is flowing, like this, this, in this manner. So what will happen actually? The molecules which are in this layer, they will be strongly attracted by these molecules from the surface, is it? So because of adhesive force. So you can see the molecules of fluid or liquid which are in contact with the layer or with the surface will be almost at rest, is it? The molecules, it can be atoms also depending on, or atoms of liquid in contact with the bottom surface or surface of the plate will be in almost rest, right? Because of the adhesive force, due to adhesive force. I am trying to understand why viscosity, from where and how it arises. Okay, so here this layer is flowing, but these adhesive force due to these molecules will oppose their motion and they will be almost at rest, is it? Like this. So this adhesive force will simply stop them. Then what will happen actually? These molecules will apply the force on the next layer. So but what will happen depending on because normally what happened, cohesive force, adhesive force is greater or cohesive force is greater, that depends on the nature of the material in contact, depending on the fluid, depending on the solid surface. But generally what happened, in this case we can consider this adhesive force is strong, so it will be strongly their motion of these first layer will be strongly opposed by this adhesive force on the bottom, bottom solid surface. And similarly, because these are at rest, so the upper layer, is it, of the molecule will be also trying to move, but this cohesive force between the layer 1, let's say layer 1 and layer 2, 3, 4, 5, 6, 7. So you can see the motion of layer 2 will be opposed by the cohesive force of by the molecules of layer 1, is it, due to cohesive force. So here you can say the motion of layer 2 will be opposed by the molecules of layer 1 due to cohesive force between molecules. So in this manner you can see the highest resistance opposition is offered by this solid surface. Next these will be almost in rest. So the velocity of layer 1 will be very low, velocity of layer 2 will be still large, velocity of layer 3 will be even higher. So what is happening, like this will be moving with the maximum velocity v0, the next layer will be moving with this little small, next will be even smaller, next even smaller, even smaller, even smaller, and this will be even smaller. This will be at rest. So this will be the velocity profile. The layer which is in contact with the solid surface will be almost at rest, and this will be moving with the highest velocity. So layer 7, motion of next upper layer will be opposed by the next lower layer, is it? Or this basically, I will say the upper layer is trying to pull or bring the lower layer into motion, or trying to improve its increase its velocity, is it? So here I can say the motion of upper layer is opposed by the molecules of lower layer. How they will oppose, that must be also clear with the help of coercive force, is it? You can write by coercive force. So the way, whenever like two solid bodies are in relative motion, one body opposes the motion of other body, and here I can say also in another way is this upper body is trying to bring the lower body into motion, is it, or trying to increase this velocity. So here you can write the upper layer of fluid is trying to increase the velocity of lower layer, because exactly they will be like fifth layer applying force on sixth layer in backward direction, then sixth layer will be applying force on lower layer in the forward direction. So sixth layer means upper layer will try to increase the velocity of lower layer is trying to decrease the velocity of upper layer. So in this manner, why? The reason is coercive force. This, because of coercive force, one layer of liquid opposes the relative motion of another layer, right? This property of fluid, of liquid, is termed as viscosity. So I hope you are understanding it properly, that what is the meaning of viscosity. So viscosity is what? It is a property of fluid by which the motion of, or relative motion between the layers of fluid is opposed, and that is termed as viscosity. Let me define it, write it. Okay, so the viscosity can be defined, it is the property of fluid or liquid by virtue of which it opposes the relative motion between its adjacent layers, is it? And that is, so here we can understand this is the bottom surface, different layers, the velocity of this layer is highest, top layer, then lower, it's decreasing, and the layer which is in contact with the bottom surface will be almost at rest. So this property, and why it is property? Because of coercive force, is it? So any fluid, any liquid which is where the coercive force are stronger, we will say the viscosity of that liquid will be higher. So viscosity normally basically depends, or I will say is proportional to density. So if density of the fluid is higher, density is higher means what? Like molecules are more closely packed, so then they will be like applying more forces on the other molecules, so they will offer more resistance, the viscosity of that liquid will be higher. So we can say the viscosity will be almost proportional to the density also. So this is like normally viscosity property, and it is measured or denoted in terms like eta, is it? So it has it is denoted by, this is eta, and its unit, so its basically unit is, SI unit is decapoise, SI unit is decapoise, right? So, and it has like CGS unit, it's poise. So different units are there for CGS and SI unit. Okay, so SI unit decapoise, and we also call like decapoise, and that is also equal to POISEUI poisely. Decapoise, poisely, both are same, and that is equal to 10 poise. Poise is CGS unit and decapoise, poisely is SI unit. So this and denoted by eta, that is the viscosity. Now here eta, like there are few more points. For liquid, the viscosity is depending, or we must be understanding it's because of cohesive force between the molecules, is it? For gases, the viscosity is not because of cohesive force, it's because of diffusion. So let me write the points about it. For fluid, for liquid, viscosity is due to cohesive or adhesive forces between the molecules, is it? For gases, the viscosity is due to diffusion, not due to cohesive force, not due to cohesive force. And we know already the viscosity of gas is much smaller than the viscosity of liquid. And so what happens actually, when temperature is rises, the kinetic energy of molecules will increase, right, for liquid. So that's why the viscosity of liquid, is it, for liquid, eta is inversely proportional to root T, temperature. As temperature increases, molecules will have more kinetic energy, the effective cohesive force between molecule decreases. So that's why the viscosity of liquid is inversely proportional to temperature. Temperature rises, viscosity decreases, is it? So viscosity of liquid is inversely related to temperature, as you can write temperature rises, viscosity fall, decreases, and vice versa. For gases, what will happen? If temperature is increased, what will happen? First thing is, gas viscosity depends on diffusion, and you must be like you must have already studied that in chemistry, that diffusion rate become faster when the temperature is increased, is it? So here I can write, for gases, temperature rises, diffusion rises. Diffusion rises means eta is also directly proportional to temperature. So for gases I can write as temperature is increased, viscosity of gases increases. And here you must be even understanding that why the viscosity of gases increases. The relation is different for gases and liquids, right? So for liquid, and I can normally write, for liquid you can write higher is density, higher is the viscosity. So you can expect, if a liquid is denser, means its viscosity will be higher comparatively. That's why, because if you just look for honey and water, right? So honey is much denser, so viscosity of honey is also much greater, or greater than viscosity of water, is it? So rho honey greater than rho water, and that implies eta honey is greater than eta water, right? That is one of the relation. So these are few points about viscosity. Let me write few more. Okay, so the variation of viscosity with pressure. So with increase in pressure, viscosity of liquid, and here remember that except water increases. Viscosity of liquid increases with increase in pressure, means directly, but for water viscosity decreases with increase in pressure, and for gases the viscosity is almost independent of pressure. So there is as such no effect of pressure on the viscosity of gas. So these are few points that you should keep in your mind, and let's continue from here onward in the next class. Thank you so much.